Hi everyone. So now in chapter 5, we are ready to look at different lapse rates in order to calculate the temperature inside the cloud. We have already looked at two different lapse rates, dry adiabatic lapse rate and dew point adiabatic lapse rate, in order to calculate the level of condensation, which is also known as the lifted condensation level after the forced lift, and it's also known as the cloud base. So you can hear it in any one of three ways. Now we're going to use another lapse rate called the moist adiabatic lapse rate to calculate the temperature inside this cloud. That is important because it helps us to predict the type of precipitation that this cloud is going to produce. There are warm clouds and there are cold clouds, and knowing the temperature inside it helps us to develop accurate forecasts. In regard to the moist adiabatic lapse rate, that is the rate of latent heat release with continuous condensation. So in other words, continuous condensation will continuously release latent energy, and in releasing latent energy, it's going to warm the molecules inside this parcel of a cloud. And in warming those molecules, you are effectively making this cloud cool more slowly. The cloud is going to cool as it rises in altitude, but it can cool at a slower rate. So the dry adiabatic lapse rate cooled off very quickly, lost almost 10 degrees Celsius per 1,000 meters. But with continuous condensation and release of latent energy, the moist adiabatic lapse rate actually cools at 6 degrees Celsius per 1,000 meters, roughly half the rate of the dry adiabatic lapse rate, which makes total sense when we think about the dry soil and the water. The dry soil really cooled off faster than the water, and the water cooled off more slowly. So in other words, why is the moist adiabatic lapse rate, MALR, less than the dry adiabatic lapse rate, DALR? It's because the condensation releases latent energy and slows the heat loss at altitude. Now, in terms of looking at the level of condensation, that requires looking at the dry adiabatic lapse rate and the dew point adiabatic lapse rate. When it comes to the temperature of the clouds, we just need to look at the moist adiabatic lapse rate. In other words, the parcel will lift with a dry adiabatic lapse rate, and we can know the temperature of the lifting parcel until it gets to the lifted condensation level. So we use the dry adiabatic lapse rate until the parcel starts to condense. Where does it condense? It condenses when it triangulates and meets the dew point adiabatic lapse rate. From there on, the lift will use the moist adiabatic lapse rate to predict the temperature inside the cloud, so that you will be subtracting 6 degrees Celsius for every 1,000 meters from the level of condensation. Now, this becomes important in a number of situations for predicting the type of precipitation from a cloud. Is it going to be rain? Is it going to be snow? And you are going to be doing an assignment that looks at the rain shadow that is the climate of the Rocky Mountains. So you are going to be predicting the condensation level, and then you're predicting the temperature inside the cloud, so you can tell me what kind of precipitation will fall as a result of that temperature inside the cloud. In doing so, let's look at what's going on. These are the Rocky Mountains. Here's the Pacific Ocean. As advection fog comes in off of the Pacific coast, it will be on a prevailing wind and advection fog, and it will literally hit the Rocky Mountains and undergo a topographical lift, a forced lift in that area. As that parcel undergoes a forced lift, it expands and cools and may condense near the mountaintop. So you see that temperatures become important here. On the other side, which is the leeward side of the Rockies, that is a what's called a rain shadow area. In this area, the parcel will now be cooled and will condense, and then it'll start to sink. And as it sinks, it will come into an area of higher pressure at lower altitude, and that higher pressure will push on the parcel to contract it. That contraction will cause all kinds of collisions of molecules, which will transfer energy between themselves. In transferring energy between themselves, they will have more kinetic energy that will warm the parcel and evaporate any remaining vapor inside the parcel, so that at the other side in the valley of the leeward side of the rain shadow, you will essentially have a dry side, a desert, due to compressional warming in that sinking parcel. The dry side, the leeward side, is what we call the rain shadow. Let's look at some other examples of rain shadows in the United States. They're common. So we talked about the one that is seen in the Rocky Mountains, right along here in the Rockies. And what we're looking at here is we are looking at inches of rainfall, very low inches of rainfall in the Arizona and New Mexico deserts. This color is very low rainfall as well. And you see that right in the rain shadow of the Rocky Mountains, as we discussed. And you also see a rain shadow right after the condensation along the Sierra Nevadas in California. So you have condensation on the windward side of the mountain and a rain shadow on the leeward side of the mountain. You'll also see a bit of this in the Appalachians, less rain on the leeward side of the Appalachian Mountains in this area. One thing that's really fascinating is to go to see Olympic National Park in Washington. I've been there myself, and this is a temperate rainforest, one of the few in the world around the 60-degree parallel in latitude, very far north. We're at about 40 degrees parallel. This is quite a bit farther north in the state of Washington. It is a temperate rainforest that is on the windward side of the Olympic mountain ranges in here, and on the leeward side of the mountains you have the Olympic rain shadow and a desert in here. Look at this. This side in Forks, Washington, where I've camped, 119 inches of rain per year. Not even near the ranger station at 137 inches of rain per year. And look over in Sequim, which is where one of the ferries goes out of, 16 inches of rain a year. And that's why the ferry goes out of there, because they have very dry, good weather and good visualization for getting that ferry across to Canada. So an astounding 100-inch difference between the two areas that are within one national park. Amazing. On the part of that as well in Washington, the Cascade and Olympic mountain ranges, this is the Olympic mountain range, this is the Cascades, provide the desertous area for the Columbia Basin and the sweetness of Washington state cherries. So these are rain shadows are agriculturally critical to understand and be able to predict rainfall. Same thing with tourism. In Hawaii, Hawaii has a rain shadow that brings in moisture on the windward side of the island on the north shore of Oahu. It condenses and rains along this rainforest on the North Shore. And then look, I've got a desert basically on the south shore of Oahu. This is Waikiki and Pearl Harbor area. Beautiful weather. So if you want much cheaper hotels on the island of Oahu, look for the North Shore of Oahu because there's plenty of rain there. And the dry areas on the leeward side have much more expensive hotels. To look at a rain shadow logically, I want to show you my drawing of a rain shadow, and then we'll start to apply numbers to it. This is a logical drawing of a mountain here, and it has an ocean here on the windward side. And in this area, we have a lot of moist air coming up from the ocean that is lifting on a topographical lift. So this moist air is supporting deciduous trees in this area. And this parcel will lift with a dry, unsaturated, dry adiabatic lapse rate, and a parcel that has a dew point that is lower. And what you're seeing here along the temperature, you have to look closely here at this temperature. Here is a 0 temperature change mark, okay? And you see 10 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius. And here what I've got is I've got 10 degrees Celsius, 20 degrees Celsius on the other side, so we can start to measure things from the top of the mountain, okay? So what I'm noting here is that the temperature of the air coming off of the ocean is at about 20 degrees Celsius. The temperature of the dew point parcel is going to be lower, right around 12 degrees Celsius here. This is how I marked it on this x-axis. Hope that makes sense to you. This will have a really steep adiabatic lapse curve. They will meet here and intersect for the lifted condensation level where my cloud will start. All right, when this cloud starts, it'll continue to rise and warm relative to the atmosphere with the moist adiabatic lapse rate. And along this area, you'll notice some pine trees growing along this area because they like the condensation and the fog in this area. This is why the redwoods grow out in California. They love the fog along the mountainous hillsides. When you get to the top of this area, you have a parcel that has warmed, risen, expanded, cooled. It comes up to the top of this mountain and it is getting dense. So it will sink down again. As it sinks down, it encounters higher atmospheric pressure that contracts the parcel and causes warming inside of the molecules. This parcel will descend down again using the dry adiabatic lapse rate to add temperature on the compressional warming pattern. So you are now adding 10 degrees Celsius per 1,000 meters with the dry adiabatic lapse rate on the parcel, really dramatic increase in temperature. And you are using the dry adiabatic the dew point adiabatic lapse rate to add dew points to this parcel as it drops down into the valley on the leeward side. Now, why do you use the dry adiabatic lapse rate and the dew point adiabatic lapse rate? Because this is 1 to 4% water vapor in the parcel, but this dew point lapse rate was always 100% water in the parcel. Therefore, there's some water still remaining in this, and it can descend using the dew point lapse rate. There's not much water at all remaining out of the 1 to 4% after all this condensation and rain or snow on the windward side. So it uses the dry adiabatic lapse rate on that side. By the time you get over here, you have a very big difference between the environmental temperature in that parcel and the dew point temperature in that parcel. That big difference means dry air. See you on the next video.